Welcome back to the NMR Challenges series. In the previous video, I provided this NMR challenge for you. And today, we are going to explain the solution step by step. If you have already solved it, then you can match your answer by the end of this video. So let's start today's NMR challenge.
This is our seventh NMR challenge, in which we are going to determine the structure of the compound having molecular formula C4H8Cl2 from the given 1H NMR and 13C APT NMR. So while determining the structure of this organic compound, we are going to follow all those steps which we learned in the last videos. So first we will calculate the index of hydrogen deficiency, then we will look 1H NMR, and after that we will look 13C APT NMR. Before solving this problem, we are going to revise all those steps which we are learning since beginning, and we will revise chemical shift value for 1H NMR and 13C carbon NMR as well. This is very important to keep revising because this practice will make you perfect. And here are those steps. So first step is calculating the index of hydrogen deficiency, which is also known as degree of unsaturation, and this is the formula. So this formula is 2 multiplied by number of carbon atoms plus 2 plus number of nitrogen atoms minus number of hydrogen atoms minus number of halogen atoms divided by 2. So the value gives number of pi bonds or rings, or it could be both. If this value is equal to 5 or greater than 5, then we can blindly say that it has one benzene ring, and this benzene ring will correspond to the 4 value because it has 3 pi bonds plus 1 ring. Then we will see 1H NMR, and as we said that number of signals is equal to the how many types of protons are there. Splitting patterns will give us information about the number of neighboring protons or substitution pattern on the benzene ring. So here is the splitting pattern formula, n plus 1, where n is equal to the number of adjacent protons which are equivalent. And for determining the substitution pattern on the benzene ring, we should also know the J coupling value. So we will learn when we will have those kind of problem. And 1H NMR chemical shift values is also very important to understand shielding and de-shielding of the protons. As I told you, primary carbons, hydrogens coming in the shielded region from 1 ppm to 1.2 ppm. Secondary carbon hydrogens are slightly de-shielded as compared to the primary, and tertiary hydrogens are slightly more de-shielded from 1.4 ppm to 1.9 ppm. And we also learned that when methyl is attached to the ketone, then it comes from 2 ppm to 2.6 ppm, and it is quite similar value for methyl attached to the benzene ring, such as in toluene. So it is also coming in the same region. Acetylene protons is slightly de-shielded as compared to the methyl attached to the aromatic rings. It comes from 2.5 to 3 ppm. This is very interesting value. When oxygen attached to the carbon, then hydrogens are coming around 3.5 to 4.5 ppm more often, and it could be higher also, but usually you will see in this range. And when it is attached to the nitrogen, then it can come from 3 to 4 ppm. We also learned that hydroxy and amines protons are acidic, therefore they can undergo exchange from one molecule to another molecule, therefore their values are not fixed, and it is coming from 1 to 5 ppm. The aromatic protons comes from 6 ppm to 8.5 ppm, sometimes overlap with the alkene protons. This depends on the nature of the alkenes. Aldehyde protons comes from 9.5 ppm to 10.5 ppm, but carboxylic protons always comes after 10 ppm to 13 ppm, and it is slightly broader signal. So we should remember these values because it is very important to determine the structure of the compounds. Then the third step is 13C APT NMR. So we will look 13C APT NMR, and we know that this NMR gives all kind of carbon signal, but in 13C depth NMR, we don't see signal for quaternary carbon, the carbon which doesn't have any hydrogen. It also tells us how many types of carbons are present in a molecule. And we also learned that methane and methyl peaks are 180 degree opposite to quaternary carbon and methylene carbon. So in this spectra which we are going to show here, the quaternary carbon and CH2 signals coming in the upward direction, or we can say in a positive phase, and methane and methyl carbon are coming in the negative phase. But remember that when you are solving in MNOVA or any other software, then you can change it. You can change this phase by yourself, and then it could be opposite. But here the NMR which we are looking, in that case we are following this pattern because those NMRs are presented in this way. It is also important to remember some of the chemical shift values for carbon. So here are some chemical shift value for the carbon. When it is primary, So it is coming up to 35 ppm. When it is secondary, it is slightly deshielded. Tertiary is coming maximum 55 ppm. When it is connected to the oxygen, then it comes from 50 to 70 ppm more often, but it could go to 90 ppm depending upon the structure. Acetylene carbon comes from 70 to 90 ppm, and benzene carbons comes from 110 to 170. These values for the functional groups is very important to remember. Ester comes from 165 to 175 ppm, but amides could be slightly lower than ester. It can be from 160 to 175 ppm. Carboxylic acid is slightly higher from 175 to 185 ppm. Aldehyde always coming in highly deshielded region from 190 to 200. Therefore, it is easy to distinguish between carbonyl carbon from ester or carboxylic acids. So after revising the chemical shifts value, now we are ready to take this challenge. So first we are going to calculate the index of hydrogen deficiency using the formula 2C plus 2 plus number of nitrogen minus hydrogens minus halogens divided by 2. 2 multiplied by 4 plus 2, 0 minus 8 minus 2. So the index of hydrogen deficiency is 0. This means that there is no pi bond or ring. Now we are going to check the 1H NMR. So to interpret the 1H NMR, first we will see how many signals are there. So there are two signals, signal A and B. Two signals implies that there are two types of hydrogens. Now we will look the integration value. If you look the integration value for the signal around 2 ppm, so signal around 2 ppm has integration value 1H and it looks multiplates. Therefore, we cannot determine the neighboring hydrogen value in this case because this is multiplates, and this 1 hydrogen integration value indicating that there is something CH. But is it true? Because if you look at the another signal also have integration 1, and in the molecular formula we have 8 hydrogen. So it means this is the ratio. This is the ratio of the integration value. So each signal A belongs to 4 hydrogen and signal B also belongs to 4 hydrogen. If you look the signal B, which is around 3.58 ppm corresponding to 4 hydrogens, it is also multiplates. Therefore N we can't determine in this case, and we can say that there is something like this, and this value indicates that this might be attached to chloro group. The integration value also indicates that the molecule has symmetry. That's why 8 hydrogens are divided into 4 hydrogen and 4 hydrogens. Okay, now we will look the carbon NMR. This is the 13C APT NMR, and the upward signals, we know that upward signals correspond to carbon and CH2, and the downward signals correspond to CH3 and CH. So now here both are in the upward direction. Therefore we can say that these signals and these signals belongs to either carbon or CH2. This compound have CH2 group, and this one could be carbon or CH2. So if you think that this is only carbon, then probably it is attached to chloro. So let's try to now draw the structure of the most probable structure of the compound. So if I put chloro on one of the carbon, then another will be CH2, then another CH3 and CH3. So how many hydrogens are there? 3, 3, 6, 8. So 8 hydrogens. Molecular formula also have 8 hydrogens. But look, we don't have any methyl signal in NMR or carbon 13C. And this molecule also don't have any symmetry. So this cannot be the correct structure. Now we can say that this cannot be quaternary carbon. So it means that this molecule have only CH2. So this carbon indicates that this molecule have only CH2, CH2. So let's try to draw the structure now. So let's say CH2, CH2, this is CH2, and this is another CH2. Now how many hydrogens are there? 8 hydrogens. Okay, I will put the chloro here and here. Let's see now. The molecule has plane of symmetry, and look at this. These two hydrogens are A type because are same, and these two hydrogens are B type. So this will show you the signal around 3.58 ppm, and integration will be 4 hydrogens, and this will be multiply. And this A type of proton going to show you the signal around 1.95 ppm, and it will be 4 integration. So we can clearly say that the given spectra belongs to this compound. Now here is the another NMR challenge for you. You have to determine the structure of this compound having molecular formula C6H10O2, and this is really very interesting problem, and we are going to solve this problem in the next video. So don't forget to subscribe my channel. We will see you in the next video. Thank you very much. Take care. Bye bye.